All right, guys, so Unit 6, this is our review lesson. I felt that it was beneficial for you guys to have this to help you review. So I'm going to show you some Regents questions that might pop up on the test, may or may not, I don't know, hint, hint. Anyway, some images here to give you a reminder of what this unit was about. All right, so we have a heating curve here. Okay, notice how it indicates when we use MC delta T versus the heat of fusion or the heat of vaporization. Solid, liquid, and gases, particle diagrams, combined gas laws, Boyle's law, Charles's law, and finally Gay-Lussac's law. Okay, so these laws apply to gases only, and only when one of the variables is held constant. So it all relates back to the combined gas law. Now, I do want to indicate to you guys, and I'm pretty sure I said this in a previous lesson, but the ideal gas law follows a couple of things in order for it to follow the KMT, we should say, the kinetic molecular theory. Okay, high temperature, low pressure is when we have a gas that will behave ideally. Okay, so I always say high T, low P, if that helps you. Now, if we look at a couple questions here, we're going to look at the first one, and it's pretty long, but it shows us two cylinders here with hydrogen gas. Identical cylinders, okay, same size, same shape, and we're going to look at the pressure, volume, and temperature of the gas in each cylinder. Question states, compare the total number of gas molecules in cylinder A to the total number of gas molecules in cylinder B. So if we remember, Avogadro's law states that gases that have the same exact pressure, volume, and temperature will also have the same number of gas molecules. So if we compare pressures, volumes, and temperatures of the two gases here, we notice that they are equal. So therefore, the total number of molecules will be equal. Let's get another question here. So this one says to state the direction of heat flow that occurs when the activated cold pack is applied to the body. So we're going to read this. It says cold packs are used to treat minor injuries. Some cold packs contain ammonium nitrate and a small packet of water at room temperature before activation. To activate the cold pack, the small packet must be broken to mix the water and the ammonium nitrate. The temperature of this mixture decreases to approximately 2 degrees and remains at this temperature for 10 to 15 minutes. So what is actually happening is that the heat is flowing from the body to the cold pack. And that's why after 10 to 15 minutes, the cold pack is no longer cold. So heat is always going to go from the higher temperature to the lower temperature. So direction flow will be from the body to the cold pack. And thus making your skin feel cold and the cold pack actually getting a little warmer. Okay? Now this question says to explain in terms of intermolecular forces. Now I did this as a warm-up. So please remember that your answer needs to be in terms of intermolecular forces. Now, if we look back here, we say, well, if we're talking about intermolecular forces and the relationship to boiling point, well, why would hydrogen have a lower boiling point? Okay, well, high intermolecular forces, high IMFs, mean high boiling points. Okay, so if it's got a lower boiling point, then it's going to have lower IMAFs. All right? Next, a weather balloon has a volume of 52.5 liters at a temperature of 295 K. And I'm writing this all out as I read. The balloon is released and rises to an altitude where the temperature is 252. So that shows me a change in temperature. Okay, what pressure in atmospheres is equal to 45.6 kilopascals? Now, we don't have to use our combined gas law here because we have... Okay, so this question is asking what pressure in atmospheres is equal to 45.6 kilopascals. And actually, if you read the question or the passage, it has nothing to do with this question. What they want us to do is convert kilopascals to atmospheres. Okay, so if we have 45.6 kilopascals, and if we look, okay, 101.3 kilopascals is equal to 1 atmosphere. All right, but we only have 45.6. So we're going to divide this by 101.3 kilopascals to give us how many atmospheres we're going to have. Because we don't have 101.3, so we need to know how many kilopascals we're going to have. Now, obviously, atmospheres, I'm sorry, we're obviously going to have less, okay? Because if 1 atmosphere is equal to 101.3, and we only have 45.6, it looks like it's about half, okay? So we're going to look at and calculate this now on our calculator. So take your calculator out, and we're going to punch in 45.6, and we're going to divide that by 101.3, and that's going to give us about 0.45 ATMs. All right, so the answer is going to be 0.45 ATMs for the conversion. And that is going to be on table A, okay? Tells you standard temperature and pressure. All right, so let's look at a couple more questions here. Number 6 says to convert melting point of the metal obtained from copper 1 sulfide to degrees Celsius. Well, let's see. Copper 1 sulfide, what is the metal there? The copper, okay? So what we need to do is look up the melting point of copper on table S. What to do is look up the melting point of copper in our reference tables on table S, and when we look that up, it's in Kelvin, so we need to just convert to degrees Celsius. When we go from Kelvin to degrees Celsius, we subtract 273. So 1358 Kelvin is the melting point for copper, very, very high, okay? That's why it's a great piece of metal to use for pots and pans so it doesn't melt while we're cooking. And when we convert it, we get 1085 degrees Celsius. Now this one over here, number 8, is set up because we're using the combined gas law. When I see pressure and volume and temperature and they ask me about volume at a different temperature and pressure, then I know I'm using the combined gas law. So the question says to calculate the volume of the nitrogen gas at STP. So that's going to be your P2, V2, and T2, okay? We're looking for V2. So P1, okay, is your 1.30 atmospheres. A temperature for temperature 1 is going to be 301 Kelvin, and the volume is going to be 40.0 liters. Now, what we want to know is what the volume is after it goes to STP. So standard temperature in Kelvin, remember it has to be in Kelvin when you do combined gas law, is 273, and we're using atmospheres, I'm sorry for pressure, so that's 1, and then we're going to solve for V2. So give yourself a chance to calculate that and then come back and check your answer. And you should get 47.2 liters. Okay? All right, next. So here we have some multiple choice questions. Which Kelvin temperature is equal to 200 degrees Celsius? So here we're going from Celsius to Kelvin, so we're going to add 273, and we'll get 473. So the answer is D. For 2, which statement describes the particles of an ideal gas based on the kinetic molecular theory? That's KMT. So remember, particles have to be small, the motion is random, and they have no attractive forces between them. So which one is going to follow that? Let's see as our choices, we go through them. As the gas particles collide, the total energy of the system decreases? No. KMT says that it stays the same. Gas particles are larger than the distances separating them? No, they are much smaller than the distances separating them. And B, gas particles have no attractive forces between them? Yes, which allows them to move freely. Okay, so the answer is going to be B. Now 3 says a 220 milliliter sample of helium gas is in a cylinder and a movable piston at 105 kilopascals and 275 Kelvin. Piston's pushed in until the sample has a volume of 95 milliliters. The new temperature of the gas is 310 Kelvin. So what is the new pressure? So this is actually P2. So we're using combined gas law here, okay? So we have 220 as our first volume, volume 1, times our pressure, which is 105 kilopascals. Now, it doesn't matter if you have milliliters or liters because it's going to get canceled out anyway. Over 275 is equal to, that's kilopascals there, guys, equal to new volume, which is 95 times P2, that's what we're solving for, over 310. So do your calculations, come back and find the correct answer. Okay, so you should get 274. D is the answer. Which unit is used to express the pressure of a gas? Well, moles? No. Okay, moles is number of molecules or particles. Kelvin is temperature. Joules or pascals? Pascals is pressure. Joules is energy. Okay, so the answer is D. Temperature of a sample of matter is a measure of the what? Total kinetic energy, total potential energy, average potential energy, or average kinetic energy. I've said it over and over, average kinetic energy. Which type of energy is associated with the random motion of atoms and molecules in a sample of air? Okay, random motion of molecules in a sample of air. Well, it's not chemical energy, all right, because we're not dealing with any type of chemical reaction. Electrical energy? No. Nuclear energy, well, we haven't even learned about that, so we're going to say thermal energy. Heat, okay? Heat is going to make the motion of the particles speed up, so it allows them to move freely and have more collisions, hence the collision theory. All right, so a sealed rigid 1 liter cylinder, this means that it's fixed, okay? Rigid meaning a fixed volume. Contains helium gas at STP, and identical sealed container contains neon gas at STP. These two cylinders contain the same number of what? Atoms, okay? Atoms or molecules. Same thing, or particles, however you want to say it, okay? But anytime that both are at STP, you're going to have the same number of molecules. Which gas sample at STP has the total number of molecules, same total number of molecules as 2 liters? Now remember, all conditions have to be the same. If you have 2 liters of CO2, then you need 2 liters of another gas. Okay, that would be B. Which sample has particles with the lowest average kinetic energy? Would be the lowest temp. That's what you're looking for. So let's look here. I have 50, 30, 40, 20. The answer is D. Doesn't matter how much you have. That is going to change the amount of heat energy you have, okay, but not the amount of kinetic energy. Which sample of energy or water contains particles having the highest average kinetic energy? So here we're looking for high temp, highest temp, okay? So we have 95, 75, 75, 25, so we're going to go with 95 degrees, highest temperature. Object A at 40 and object B at 80 are placed in contact with each other. What statement describes the heat flow? Well, remember, from high to low. Okay, so what's going to happen is the heat is going to go from B to A. All right, heat flows from object B to A, always. Cylinder with a movable piston contains a sample of gas having a volume of 6 liters and 293 K and 1 atmosphere. What is the volume of the sample after the gas is heated while the pressure is? So this is combined gas law. I'm going to abbreviate it, CGL. I want you guys to set it up, calculate it, and come back and see if you get the answer correct. Okay, you should get 6.2 liters. All right, moving on. A real gas behaves least like an ideal gas under the conditions of what? I said high T, low P, okay? Or high T, low P. Okay, so that's what we're looking for. High temperature, low pressure, C. Remember this. Remember, which temperature is equal to 120 Kelvin. So this is going to be 120 minus 273. So you know you're going to get a negative number, and you're going to get minus 153. So the answer is A. What occurs when a 35-gram aluminum cube at 100 degrees is placed in 90 grams of water at 25 degrees Celsius in an insulated cup? So think about this. It doesn't matter. Mass does not matter. Remember, heat goes from high to low. Okay, so we're going from here to here. So the heat is going to be transferred from the aluminum cube to the water in the cup. Okay, so heat is transferred from the aluminum to the water, and the temperature of the water is actually going to increase because the heat's going to the water. So the answer is B. And finally, okay, we have a question here. It says, what is the correct numerical setup? And I scribbled that out. But correct numerical setup, guys, for calculating it. So what you're going to do is P1 V1 over D1 equals P2 V2 over T2. Okay, and we're going to plug all this in. We have initial. That's all your P1s, V1s, T1s, and then final. All right, so Pressure, 2.0, times volume, 500, over temperature, 200. Make sure it's in Kelvin, which it is, so we check that, equals. Okay, now we're looking for the new volume. We're looking for V2. And then we have 300 on the bottom for our temperature and 7.0 on top. Now what you're going to do is you can rearrange this so we know what we're going to get. Okay, and so what happens is we have to get V2 by itself. So what we can do is multiply the top by 300, okay, and then divide by 7. So the answer is going to be C. Okay? At STP, which 2-gram sample of matter uniformly fills? Uniformly, meaning filling, nice and even, filling it out, okay, uniformly. Well, let's look at our phases. We've got liquid, solid, aqueous, and gas. Well, this is not a phase, okay? Aqueous is not a phase. Remember, that's going to be a liquid. Bromine, liquid, is not going to uniformly fill it. It's going to be down here. Liquid's going to be down here, okay? Solid will probably fill it if it's completely frozen, but I don't think that's going to be the case. It's a closed container, so we're going to go with a gas. So the answer is D, okay? And this question here, again, correct numerical setup for calculating volume, same idea, okay? P1 V1 over T1, P2 V2 over T2, okay? And you could do that on your own. Which substance has the lowest vapor pressure at 75 degrees? This you need to look at table H. Okay, so what I did was I went ahead and answered these questions for you, and I'd like you to review the question, and if you have any questions you can ask me in class. But remember here, which segment represents gas phase only? That's going to be A to B. This is cooling, so gas, and then finally solid down here. At STP, 4 liters contains the same total number of molecules as anything else that has 4 liters, so that's what you're looking for. Which physical changes are endothermic? Absorbing heat. So remember, it's on the heating curve. Which way? You're going this way on the heating curve. So that's melting and evaporating. Which forms of energy is, or which form of energy is converted to thermal energy when propane burns in air? Well, when you heat something up, you're actually going to turn it into chemical energy because now you have a new product being formed. So that's chemical. Which line? Okay, we did that one. The concept of an ideal gas is used to explain the behavior of a gas sample. That is the whole point of KMT. Okay, which graph represents a relationship between volume and Kelvin temperature for an ideal gas? So what you want to do is, this will help you out, but this was on the video lesson. If you hold your finger on one of these, whichever one is constant, so here it's going to be pressure, okay? If you increase one, the other one's going to increase, so it's a direct relationship. So what we're doing is we're going volume over temperature, or temperature, yeah, volume over temperature, and we get an increase, okay, in a direct relationship. Which graph represents the pressure-volume relationship when we're at constant temperature? So using this, put your finger on the temperature. If pressure increases, volume decreases, so it's an inverse relationship, so we're going to go with D, inverse. Okay, and which Kelvin temperature is equal to negative 273? We add 273 to that to get 200 Kelvin. And finally, please be sure to look over all of your notes for this unit. You're responsible for everything in the note packets and the practice packets. So please have any review questions ready for class prior to the unit test next week.